Hello everyone, welcome to my session on PASS Summit 2012. My name is Fabiano Amorim. We will talk about unexplained memory problems in SQL Server today. We will see a couple of problems and dig into those problems and learn more about the troubleshooting process of trying to understand a memory problem. Right, it's like I mentioned, my name is Fabiano, and if you're watching the record of this presentation, feel free to drop me an email with questions, and I'll be more than glad to help. All right. Okay, let's move forward because we have a lot of things to do today and to cover, and I do really want to cover all. So I don't want to spend too much time on those initial slides. So a few things. Explore everything else that PASS has to offer for you. So if you have never went to a SQL Saturday, for instance, look for it. They do tons of events all over the world. So feel free to do it. Of course, with this whole COVID thing, most of the events are online, which is good because you can attend an event in in a country far away from you. So explore the free content of PASS. Please, I do take evaluations in consideration, and I look at all of them, and I try to improve the content and the way I speak and the things that I'm speaking of. So please submit your evaluation, and don't be afraid of telling bad things about my session. So those bad things are usually the ones that are more useful for me. Okay. All right. So just a little bit about me. I don't want to spend too much time here. My name is Fabiano. I'm based in Brazil. I work as a project engineer at PTN. So we do database consulting. Most of the things that I'm working on are related to SQL Server. I've been working with SQL Server for several years, and I'm an MVP for 10 years. So since 2011, so I will be 10 years next year. So feel free to download the few books that I wrote. Just go to the blog fabiano.com and download the PDF. And that's all I have. By the way, that picture, it's really old. Well, it's not that old, but it's very different than what it looks like right now, right? But anyway, I gotta update this one, I know. Let's move forward. So the agenda today is really straightforward. We will look at two cases and analyze the problem of those two cases, right? And hopefully we'll have some time to discuss about those problems in the end. I will try to leave a few minutes in the Q&A. Reminder, and this is an important reminder, this is a 400 level session. That means that it's an advanced session. So even though I usually try to explain basic things, I might don't, right? So be prepared. If I mention or if I say something that it's too advanced, and if you don't know it, you can read more about it and then come back to this session to see. And you can always send me emails as well asking for more information if you want. Okay? All right, let's jump into the problems and start to the fun things. So here's what we have. I created this VM here and prepared the two scenarios we were going to analyze. The first memory problem we will analyze is this one. It's what I call the case one. And let's prepare the demo here. So just follow the steps here to prepare the demo if you want to reproduce the problem in your own machine. I'm running this in a SQL Server 2017 and using the latest cumulative update. And my server, I will give it 50 gig of memory, has the max server memory. Okay. All right, so just to confirm that I have the 50 gig, and I want to test it starting from the code cache, and so I will restart the instance to have the worst scenario where I would have to read the data from the disk, right? And then while it's restarting, here you have the scripts to create the databases and the tables that I'm going to use in this test. Okay, you can create yourself. I already did it, so I won't wait 9 minutes to script to run. This is pretty much going to create two databases: the app DB and the stage DB, and several tables inside the database, and we use those tables in the demonstrations. So here's the script, and then let's go to the script case 1.1, which is showing the issue. So here's the scenario we have. We have a customer complaining that after developers applied a new integration services package, the application that has nothing to do with the package, it's a different database, started to show general slowness, and queries were taking forever to finish, and even sometimes the application wasn't able to even to connect into SQL Server. So the instance was really slow, and they want to understand what happened and why it only happened when the developers applied the new package. So what caused the problem and what is the problem? And this is what I want to show here, how to troubleshoot a memory process. That might be very different depending on the problem, but this is what I did. So to simulate the issue, just restarted the instance, so I don't need to run the step one again. So I will start by read some data and insert this data into the buffer pool data cache. So this is the first time I'm reading this 16 gig table. So it might take 44 seconds to run because it is going to read all the data from disk and then insert and put them in the memory. Then I'm going to read a few other tables. So this is table 1, then I will read table 2 and 3 and 4, and this is about 40 gig total of data that I'm going to read. I have 50, so we still have some free memory available. So let's run it. And while it's running, let's look. It's probably going to take 44 seconds, right? And while it's running, I have resource monitor opened here. And as you can see, this is pretty cool, isn't it? The performance here, it's really nice. I'm reading from the data file about 400 megabytes per second. That's really cool. Even though the response time is not that bad, it's not that good, but it's okay. 400, I can live with that. So it's probably going to take the 44 seconds to run, and I will speed up the video because I don't want to wait, keep you waiting here. So I will speed up the video, and we will get back in a second for you to continue the demonstration. Okay. All right. See you. Okay, so it finished and we are back. And all right, so if I read the tables again, it should read really fast, right? Because now it is going to read it from memory. Let me just confirm that I just read everything. Okay, let's see. All right, yeah, it took only 1 second to read all the data. That's perfect and expected because data is in memory. If we look at the memory clerks, we see that the buffer pool clerk is using about 40 gig, and that's okay. Now, I'm going to run this job here, and what the job it is going to do is to run a package, an integration package that is going to read the flat file and insert the data into a table inside the TempDB database. Okay. Let me run it. This is the job. Start the job. And all right, it's running. And it's probably going to take about 1 minute to run. And we will get back again. I will speed up the video and we will get back in a minute and to continue the demonstration. All right, we are back and the job finished. Let me close this. It took about 1 minute, right? Let's just confirm how much time it took. Last execution, yeah, 1 minute, 19 seconds. Okay, that's perfect. Let me close this. All right, so now let's try to read the table 4 again. This is one of the tables that I already inserted the data into the buffer pool data cache, right? So let's try again. So I would expect it to read from memory, and it is, because it's taking only it's taking 0 seconds to read it. And if you look here, the statistics IO results, we see that there's no physical reads going on, all the logical reads. If I try to read the 16 gig table, let's see if the table is still in cache. If it is not in cache, the worst case scenario that is going to take 44 seconds to read it, right? Because it is going to read it from disk in that case. So it is running. And let's see. Well, actually, yeah, it's already 12 seconds, but I could enable the live query statistics here to see, to track the status of it, but I will do it for the next one. 28. Let's wait for 44 seconds, and it should finish. Okay, it's done. 42 seconds. That's perfect. So it is indeed reading from, well, actually, it did physical reads, right? Yeah, it read. That's why it's taking 44 seconds. It's reading from disk. That's okay. So far, so good, right? It is not, I don't see the problem yet that the customer is complaining about. They are complaining that once they run the package, things get a lot slower. Let's try to read another table now. And this table is another one that has 16 gig. Now it's a table 2. And now I will enable live query statistics. And let's see. Again, this is the same data from the table 1. So the same size, worst case, it would have to take 40 something seconds, right? There we go. As you can see, in the beginning, it was a bit fast, but now looks like it is kind of stuck at 7%, you see? Let's wait for some time. And while it's running, you saw here, this is going to take forever to run, more than 46 minutes. And why? What's going on? And this is the problem I want to investigate. What's happening here is that this query is not only trying to scan the table and read the pages from disk and save it in the buffer pool data cache, but because there's an internal memory pressure, because the job that I ran created a table in the tempdb and that used memory as well, but so all the buffer pool it's full. But what happens when the buffer pool is full and you need pages, free pages to insert and to read more data from disk? Well, lazy writer will kicks in and start to go through the buffer pool and remove some pages and from the buffer pool data cache and put them into the free list, right? So the query can read the data from disk and use those free pages. This is exactly what's happening here, and there's no problem with it, except for this case. There's one other thing that lazy writer is actually doing. It's that before it removes the data, the page from the buffer pool data cache, if the page is dirty, it has to flush the page into the data file? Well, usually the process that does the flush is the checkpoint. But the automatic checkpoint doesn't run for tempdb, except for cases where you hit the 70%, I think, of the log file, and then checkpoint will be executed. But there's no automatic checkpoint for tempdb, and there's no need for it, right? That it doesn't make sense, because the whole idea of have checkpoint running every once in a while is that to avoid the recovery process to take longer. But there is no really need for a recovery process for tempdb, because the database is recreated. Everything will be recreated. But LazyWriter, it's actually flushing those pages from tempdb into the tempdb data file. And this is taking forever. So to be able to give free pages to this query to continue to run, LazyWriter is actually flushing pages from tempdb into the tempdb data file. And this is the one that is causing the problem, right? I will stop this because it's going to take forever. And let's open another file here. It's this one, understanding the problem. And I have the whole explanation and a few things you have to remember if you don't remember, like a checkpoint, what it does, or indirect checkpoint was enabled on 16 for model. And since tempdb inherits model, it has indirect checkpoint enabled as well. But indirect checkpoint doesn't flush pages created by non-booked or minimum logged operations, which is the one that is the case for the package that I'm running. I'm reading the flat file and inserting the data into a table. That's a minimum logged operation. So that means indirect checkpoint, even though 16, indirect checkpoint won't flush those pages. Usually, for a regular database, eagerWriter does flush the pages for minimum logged operations. But on SQL Server 2014, this was changed, and eagerWriter was kind of relaxed, and it is not writing the pages of minimum logged operations for tempdb anymore. That means that your book insert, it's all in memory. It's all inserting data into the memory, and if there is not memory enough, it's going to steal from the buffer pool and insert the pages in memory. All the pages will remain dirty because it's tempdb. There's no checkpoint. There's no indirect checkpoint for those pages. And eagerWriter is neither writing them to data file. But then what happened is that you have the buffer pool full of bunch of dirty pages from tempdb, and now you have an internal memory pressure, and LazyWriter, it's grabbing those pages and flushing them to the disk. Does it really have to do it? I don't think so, right? Especially because in that case, the page, the table that I created doesn't exist anymore. So in the package, I'm reading the file, inserting to the table, processing something, and then deleting the table. So, but the pages that I allocated in the process are still there in memory. And LazyWriter is grabbing those pages and is flushing it to tempdb file. So flushing data of a table or of a page that belongs to a table that doesn't exist anymore. LazyWriter should be smart enough to grab this page from the buffer pool. If it is dirty, before it flush it, check if it really makes sense to flush it because the object doesn't exist. If it doesn't, just grab the page and put into the free list and we are good to go, right? Even though it's dirty, if you replace the content, who cares? No one needs this information anymore. Anyway, this is what's happening, right? That's the problem. And there's the whole explanation here. And just want to highlight one thing. I read it again. Let me restart this to start with the cold cache. And here's what I'm doing. I will, let me include the actual live query. I will populate the buffer pool data cache again. And now I will run the old version of the package, the one that inserts the data into the StageDB table, not into the TempDB table. Okay, so this one is the one that is lower, and the developers changed the package to use the optimized version, which is the one that using TempDB, and it is faster because it is not writing to the data file anymore, right? So remember, if you book insert into a table that is part of a user database, eGetWriter will do flush those pages into the data file while it's running. But if it is for the TempDB, it won't. So you're pretty much comparing one thing that is inserting to a physical insert into a file and another one that it's inserting only in memory, but causing another problem later, that because those pages are all in memory, in a memory pressure, they will have to be flushed by LazyWriter, including for pages that, like I mentioned, doesn't belong to an existing object. All right, I think I restarted the instance. Let me run this, and I will, again, speed up the video, and we will come back in about 2 minutes, okay? So see you there. All right, it's done. And now, here's what I'm going to do. I have a performance file. It's already opened here. I'm capturing a few counters that are going to be important for us. Before I run the package, I want to see exactly how much data this is writing to the data file. So I'm going to create a snapshot of the IO virtual file stats, run the package, and then compare what changed with the snapshot that I capture. So let's do it. So this is my snapshot. All right, let me run the job. But now I'm going to run the version that it's actually writing to the user database table. This is going to take longer because it's going to write into the file, right? The data file. eGetWriter is going to write into the data file. Let's run it. Start job. Let's just, yeah, it's in progress. So it's running. To confirm that this is actually writing to the file, we can easily come here to the resource monitor. And I already can see that it's reading from the flat file, and it is writing, you see, 14 meg per second. So it is writing to the data file. This will not happen with the TempDB because, again, eGetWriter will not write those pages. So that's why it is going to be a lot faster, but it is going to cause a problem. So all those pages that are being written into the data file are clean because the eGetWriter it's cleaning them. It's flushing, persisting the data into the disk. If we come here and look at the buffer descriptors while it's running, let's open a new query here. Buffer descriptors, let's see. Most of the pages for the StageDB database should be clean. Yeah, they are. So I already have about 3 gig, and most of them are clean. So there's a column in the buffer descriptors called is modified. As you can see, most of them are clean. Do we have? Yeah, we do have a few dirty pages for the StageDB, but just a few. In a memory pressure, if LazyWriter needs to remove those pages from the buffer pool to give room for other pages, it's easy. It's just grab it and put it into the free list. But for the TempDB case, because the pages are dirty, it has to flush it first. And that's what causes the problem. Okay, so it's running. I won't wait. Oh, there's one more thing that we can look here. I have a counter here, the bulky cop rows per second, and it's about, I'm copying about 8,000 rows per second, and the throughput, it's about 51 megabytes per second, which is okay, right? But if I stop it, I won't wait. I will stop it. I think that it's already enough. Let's stop the job. Okay. So if we look here, let's see the snapshot. So for the time this was running, it wrote about 8.7 gig into the data file. If I try the same thing with the optimized version, with the one that inserts into a TempDB table, here's the difference. Again, let's capture it. Okay, and now let's try the TempDB version. Let's wait for it's in progress. Okay, it's running. And let's look at the resource monitor again. As you can see, not much going on into the TempDB file, right? No reads into the TempDB file. It's pretty much reading from the flat file and then inserting the data in memory. Let's look at the performance counter here. Here's the difference. The throughput now it's about 324 megabytes per second. How many rows? Here's the difference. This was the one that has eager writer writing, flushing the pages, and this one it's all in memory. It's inserting 40,000 rows per second. That's perfect. That's the best performance you would get because all the data it's in memory. Well, but at which cost? Well, if we look again at the buffer descriptors, look at this. It's going to take a few seconds. There it is. Our TempDB is the top one. It's already using 22 gig of memory and all the pages are dirty. In a memory pressure, Lazy Writer will have to flush some of those and write into the TempDB file might take some time. And that's what's happening in that case. Let's come back here. What else do we have? Yeah, if I try now, it's probably done, isn't it? Yeah, it's done. If I try to read the tables now again, I will cause the internal memory pressure, and then this is going to call Lazy Writer and cause a problem we know. But now let's run it. And while it's running, let's check a few things. I have those DMVs that I want to check with you. So the session is 57. It's running. It's selecting the table 1. I'm also looking at the wait stats and the pending IO requests. Let's see what we have here. Well, so far the pending IO requests, we are only seeing reads for the appdb, which is fine. It's reading the data from disk, and then eventually we have to put information in memory. Let's run it again. There we go. Yep, I'm trying to read the table 1, and here's the wait. Sleep, bpool still. It's waiting, it's sleeping while wait for the buffer pool to steal a page from the buffer pool. And you see that it's running in parallel, so we're having the waiting tasks, many threads here. Most of the threads are waiting for the buffer pool steal thing. And the pending IO requests here are already showing us 480 pending IO requests for the TempDB. If we look at the resource monitor, we should probably see here, yep, TempDB, something is writing data into TempDB now. So that's really weird to see, right? You have a query that is running. The query is actually selecting something only. It has nothing to do with TempDB, and it is waiting for the TempDB, right? What? Yeah, that's what's going on. Lazy Writer, it's running. If we look at the performance here, I think I have the Lazy Writer counter here. Yeah, you see the Lazy Writer, it's running and it's flushing the pages to TempDB before it put them into the free list. This is really interesting, isn't it? So what else can we see? I like this one. We can see what's going on in the stack, the thread stacks. So I'm going to open the Windows debugger here, and let's look what's going on. Let me clean this. Unique stack. This will dump all the stack for all the threads. And let's see if we can find something interesting here. There we have one thing that is interesting. So remember, you read it from here in that direction, from the bottom to top. So it is starting the query, blah blah blah. Oh, it's asking for some page reads with read ahead, and then it's calling the buffer pool to do the read ahead, and then getting the from disk, and then steal. Oops! Now I have to steal a page from the buffer pool because it probably has an internal memory pressure, and then it is going to sleep while it's waiting for the steal, waiting for the buffer pool steal. Do you remember that wait that we saw before? The name is really similar, right? Waiting for the steal in the buffer pool. Yep. Then you wait, and someone will signalize you once the operation is completed. Let's see if we can see the lazy writer running here. We do have other threads because it is running parallel, right? So we will probably see many of those. And this one is interesting. And after it calls the steal buffer pool, it is running the replenish free list. This is the method that get pages from the buffer pool data cache and put them into the free list. So this is lazy writer working here. That's nice. Here is then it's writing, it's flushing the data, and then calling the write file win32 function to do probably the async, right? And then it's going to wait. Let's see if we do have I want to see the lazy writer, the thread for the lazy writer. Let me search for it. Lazy. Where are you? Yep, there we have our lazy writer thread. And this is interesting. You see that under the file control block method, we have a get IO duration. This is important because there's a control that if the IO in the disk is too high, the number of outstanding IO requests can be reduced to minimize the impact into a busy environment. So you don't want, here's what this is doing. You don't want lazy writer to cause you IO contention. And this is SQL Server being helpful with you, being friendly with you, avoiding this problem. This is really cool. All right. Yep, this is it. I want to show for this demo. And yeah, I hope it was interesting. Let me release this and come back here and stop that thing that is going to take forever. Let me see if I forgot something. No, probably not. Blah, blah, blah. Oh, we might have a thread calling for the lazy writer help. Let's see if we have help here. Yep. If a thread needs memory and lazy writer, the lazy writer runs every 1 second. The lazy writer thread wakes up every 1 second and do the lazy writer thing, check if the free list it's okay or not. But if any thread needs to have free pages, any thread could call for the lazy writer help and then wake up lazy writer and create another thread for the lazy writer. So this is the help lazy writer being called by a regular user thread, not the internal thread of SQL. Okay, so let me break this in the attach, the debugger, and close this one, and close this one. And let's go to the next problem. So the next problem, again, preparing the environment, just confirming that I have memory, and then restarting the instance. Let me restart instance. And I'm calling the prepare demo file. Then I will show the issue and then understand the feature. Let's see if it's already back. It is. Let me confirm. Yep. So again, I'm creating a few other tables here. You only have to do it once. And then I'm also reading a few tables here to fill out the whole cache. So I have 15 gig available. I'm reading a bunch of tables here, enough to fill out the whole cache. So I want a hot cache, or a cache that it's already hit the target of the max memory. Okay, so this is going to take a couple of minutes. I'm going to speed up the video and see you in a few seconds. 2 minutes for me, in a few seconds for you. All right, let's wait. Hey, wait, while this is running, sorry, we understood the problem, but we need to talk about this, right? The first case problem. What would you do to avoid this problem? Because this is very, very common. What I'm saying, that it's very common that you have a scenario like this. You look at the buffer descriptors, which is the database that is taking most of your data cache, TempDB. TempDB is going to be there. This is very, very common. This is a print screen from one of my clients. And as you can see, TempDB was using 49 gig of my memory. Do we really want this? Probably not. And probably most of those pages are dirty. So in an internal memory pressure, we have the same problem. Lazy writer will kicks in, will flush those pages. I don't want this, right? Because I don't want to flush those useless garbage pages. Unfortunately, there isn't many things you could do. Things I think you could try is to make sure TempDB files are in the best disk available, because you want this flush to be the fastest as possible. You could also create a job to run the manual checkpoints every once in a while in the TempDB. That would help to reduce the number of dirty pages on TempDB. Or you could wait for Microsoft to change it and to create something to help you with that. Okay. All right. So coming back to the case 2. So I already have here the prepare demo ready. Let's open the showing the issue. And here's the issue. A customer is complaining that a report it's doing that it's taking too much time to complete. After an initial analysis, they identified that a query that it's doing some large scans. The query is reading about 400 gig, but all the tables should fit in the available memory. Still, sometimes SQL Server is doing physical instead of logical reads. You're asked to investigate the problem and provide more details. So you have a query that it's reading 40 gig of data. You do have 15 gig available, you see? We do have 51 here. If we look at the counter here, total server memory, it's 51 indeed. So we do have 51 gig available. But if I run this query, and let me enable the live query, this is going, of course, if it is the first time I'm running the query, it might do some physical reads, and then put the data into the memory buffer pool data cache. But if I run it again, I should expect it to read the data from the memory, right? Not physical reads again. And this is what is happening. I'm reading it. Let me run while I'm speaking. So I'm reading those tables. So 16 gig table joining with the 3 gig table and another join with the 16 gig table. So 3 tables, total of 16 plus 3, about, let's see, 35 gig total. I'm looking here at the size of each table. And if I scan the whole thing, all the pages, total will be 35. So I do have more than 35 gig available, okay? So they should be there, right? If in a case of an internal memory pressure, SQL Server will have to remove usually the oldest page from the buffer pool and insert the newest pages into the buffer pool, right? So usually the replacement algorithm is going to remove the page with the oldest last accessed time from the buffer pool and keep in the buffer pool only data that you're accessing often or more recently, right? So the query is running. First time it is going to take all the 1 minute and 34 seconds. Yep, it finished. It took 1 minute and 34 seconds and it did all the physical reads we were expecting. That's fine. We already know how big they are. If I run the query again, we should see logical reads, right? I just ran it. Let's try again. And it's still running. Well, I can already tell you that it's not doing logical reads because it's taking too much time. If it was all in memory, it was probably going to have finished already. And if we look at the resource monitor here, we'll probably see, yep, there we go. We can see that it's reading from the appdb file. So it is indeed doing physical reads. Again, if we look at the performance counter, we can see that the page reads here, it's showing that an average of 53,000 page reads per second. This is reads from disk. Yep, it's reading from disk. But the question is, why? Why does this reading from disk if I do have enough memory to save all the information in the buffer pool data cache? It doesn't make sense. Yeah, let's see. The buffer pool data cache. Yep. Let's open the, while it's running, let's open the understanding the feature file. Let's wait for it to finish. It's almost there. 95%. 99. Yep. 1 minute 34. Again. Probably, yep, a lot of physical reads. So we should do logical reads instead of physical. We should read it from memory instead of disk. So the golden question is, why instead of, let me prepare this again. Restart. Okay. Yep. So the golden question is, give me a second. It's back. I wanna leave it running while I'm speaking. All right. So the golden question is, why for the second execution it wasn't doing logical reads? For some reason, in the first time I ran the query, the data was not inserted into the buffer pool data cache. So the question is why? Why the data wasn't inserted into the buffer pool data cache, considering that I do have enough memory to hold all the 35 gig of data that I'm reading? And the answer is that something else should it's using the buffer pool data cache that has a higher priority than the pages you're trying to read. So kind of if you had ability of tell SQL Server, leave those pages, leave those tables in memory and don't remove them in case of a memory pressure. You know, you could do like the pin a table, but that's not what I'm doing here. That's not what's happening. In fact, there's a thing called disfavoring, page disfavoring, that SQL Server does automatically for all the scans that it thinks are going to read more than 10% of the available buffer pool data cache. So max server memory 15 gig, 10% 5 gig. If your scan is greater than 5 gig, then I will disfavor your page compared to the other pages that are there. And what disfavor means is that the timestamp, every page in the buffer pool data cache, actually it's not in the page, it's in the buff structure. So every page in cache has a buff structure. In the buff structure, there are many informations. One of them is the when this page was last accessed timestamp. And what's happening for disfavored pages is that this field it's set to 1 hour behind. It's set to back to 1 hour. So the idea here is that to avoid huge scans, to take almost all of the pages, take out all of the pages that are being read really often from the buffer pool. So let's say you have a query reading the customers table every second, and now you are running a report that is going to read a huge history orders table, and you don't really want that scan to remove your customers' pages from the buffer pool, right? It would do if it doesn't have this technique of disfavoring the pages. Because if you have a memory pressure, an internal memory pressure, and you're trying to read something, again, the buffer pool replacement algorithm is going to work and remove from the buffer pool, first of all, the pages with the oldest last time accessed timestamp. And this is why this is always doing physical reads. When it has the memory pressure, instead of removing the other tables from the buffer pool, it is actually removing the pages from the same query. For instance, if we look at the query again, let's run it. If we look at the query again, my bad, let me enable the live plan. This is reading the table of 3 gig, and then a scan in the 16 gig, and another scan on the 16 gig. So at the time I'm reading this page, the page that I just read here, it's probably the good candidate to be removed from the buffer pool. And at the time I complete the query, if I run it again, the same query caused an internal memory pressure of those disfavored objects. That this is what's happening. That's why you're seeing physical reads every time the query runs. And you can actually see this is happening on the extended event. There's an extended event called the leaf page disfavored, and this is going to tell us when a page read was disfavored, was updated with the disfavored value in the internal buff structure that I mentioned. So the query is running. While it's running, let me create this event, X event. Okay, now let me start this and let's watch the live data. The query is still running. Let's see if we can grab, oh, it's done. Okay, let's run it again. And here in the watch live data, you should, let me stop because it's going to dump a bunch of things here. Yep, we can see that this query caused the leaf page to be disfavored, and this is the page ID. Yes, I know you'd have to go to do your thing to identify which object this page belonged to, but that's fine, not a big deal. Right, so you could monitor this X event in your environment in case you want to see if you have big scans, probably greater than 10% of your available buffer pool, and see if you really want to have those pages disfavored or not. You might don't want them to be disfavored because if the data is in memory, the query will be a lot faster. Yes, at the cost of removing other pages from memory, I know, but it's really up to your business to decide which query has higher priority. If that report is the report that your big manager runs and he needs information as soon as possible, you might want to give it priority over other tables. All right, let me stop this. And just to make it more fun, let's look at this last time of access field that I mentioned. I mentioned that information, it's in the memory, in the buff structure for the page. So remember, every time you access a page, if it is not in memory, SQL Server will read it from disk, allocate a page, and insert information into the memory, into the buffer pool data cache in that case. And that page has a buff structure. It's another memory structure that has information about that specific page. One of the information it has is the BUse1 field. This is the one that will tell us when the page was accessed. What was the last time the page was accessed? All right, so let's start this again with the code cache. So checkpoint and drop clean buffers to remove everything from cache. And then I will read a table that will not trigger page disfavoring. This has only 4 gig. I have 15 gig available. This is less than 10%. So let me run it. It should be really quick. And then I will use the DBCC buffer to dump me one, you could put here a bigger number, like 50 pages from this database, this specific table. I just want one, and I'm enabling the trace flag to see the results here. Let's see. Oh, it's already here. All right, and here's what I have. You could grab the same information from the DBCC page as well. I think the DBCC buffer in that case it's easier for me. Because I want a page, I don't care which page. I just want, give me one page that it's in memory for that specific object. And I want information about what is the buff structure address, memory address for that page. And I want to see the BUse1. So this is the buff structure. Let me copy and paste it here. And the page, what is the page number? This is the page number, and in the BUs one, it's this one, 22,505. So this is the value that is going to tell us when the page was accessed. This is used based on the MS ticks from the OS sysinfo column. If you look here at that column, this is going to return to us what was the last time the computer was restarted. So the computer, in that case here, I started that VM at 9:21 a.m. And based on this, if we add this number of seconds, we will have the timestamp, right? So it kind of relies on this column to do the math and calculate the timestamp. So if we grab here this value and add this number of seconds into this 9:21 a.m., we would have this is the timestamp, the last time that the page was accessed. Okay, so at 3:36, so a couple of minutes ago. This is nice, isn't it? All right, let's try to read the table again to see if it really changed. So if I read the page again, now I'm doing a scan here, so it is going to read that page of that table. Let's see if it changes. So the value was 22,505. Now it's 22,652. So yeah, it changed with the timestamp of when I ran this specific command. Actually, the timestamp is for this command, but we will get there. All right, that's cool, isn't it? But this is a page that is not disfavored, right? If we read a table that is actually going to cause the page disfavoring, what I would expect is, instead of have this, I would expect to see this, right? And then when lazy writer runs, and then the clock hand, and then the buffer pool replacement algorithm runs, it is going to grab the oldest pages first, and then this is going to be a candidate to be removed. All right, so let's look at before we look at the page with the disfavored value, let's look at the same value in the debugger, just because we can, and because it's fun. So what was the address again? Let's see. This, I think I copied, didn't I? I think that was the address for the page. So let's, actually, I ran it again, didn't I? No, let me run it again and grab it. Let me release here. Let's run it. So this is the address for the buff structure, and let me copy the BUs1 value. Let me update here. All right, so I want to dump the data from this address. Break, and then DP, and then the address, and then this is what we have. And then this is the information that is stored into this memory address. If I run the query again and dump it again, we could compare to see what changed inside this structure to kind of be able to identify which value here corresponds to the BUs1, right? So let me run the query again. Oops, let me release here. All right, done. And then break. And then DP again. And then let's see. This is the same. This is the same. And A, there we go. So looks like this is the position of that has the information that we need, the BUs1 information that we need. We could actually grab this hexadecimal value and convert into a decimal to see. Yep, the valued expression is 22832. This is the BUs1 that is stored into the buffer structure, the buff structure. That's cool, isn't it? Okay. But, all right, let me run it again. The buffer pool here, the BCC buffer. Let me go. So if I run this, the value that I have here, it's 22906. Okay. If I look at the buff structure now, I have the 4B6A. This is 19306. This is, sorry, I want to paste it here. This is different than what the BCC buffer is showing us. Yes, it's different because it was updated again after the results were printed by the dbcc buffer command. So dbcc page and the BCC buffer will also count as a read, right? You're asking for read the page and dump the data, the content. This is a page read, right? It is going to update the BUs1 value. And it is going to show us the value for when I ran this command. But this is also disfavored pages. So if you want to disfavor a page from a table, here's what you could do. You could run the dbcc buffer for all the pages, and then all the pages will be updated as disfavored. All the BUs1 will be updated with 1 hour back. I don't know why we would do it, but that's one of the ways you could do it. And that's why the value we are seeing here, that it's currently in memory, it's different than the one that this was printing and showing us. So to confirm this, one thing that I did, I want to see when that buff structure was changed. Because I want to know when the page was disfavored, was marked as disfavored. And to figure that out, one thing that I did was I got this memory address. So we have this memory address, and we know this position of this memory address is the one that is going to be changed when the BUs1 is updated by any reason, by a query that is reading the table and reading the page, or the BCC that it's calling something to update this value. And what I did was that I added a breakpoint into that specific memory address. So every time anything that I was trying to read or write into that specific memory address, I want to break into the buffer, into the Windows debugger. And then I would be able to see exactly which stack, what was going on, what was calling the access into that specific memory address. And to do this, I would have to grab this and paste it here and add a BA. And then I think I have the command here. All right, where are you? Where are you? BA, and then R4. I want to see all the, and then a command. So BAR4. And I don't want to access this one because the position is actually this one. So this, oh, my bad. This is actually 8. BAR4. That should work. Okay, let me breakpoint list BL to show the breakpoints. So I do have a breakpoint every time any of the four first bytes of this memory address it's accessed, it should break here in the debugger. Let me go. Okay. Now if I select the table, select star from, let me count. This, well, this is actually not going to, no, not a stable. Yeah, was it a table? I just want to confirm that we are working the same table. Yeah, this is the table. So my bad. I don't want to waste time with the comments now because I made the comments for you to make it easier for you to read the file later. So yeah, this is the one. If I read this, yeah, this is the one that has that page. And because I'm trying to read the buff, it is going to break because something is trying to read the value of that buff. And see, let's see what happened. Yeah, there is breakpoint hit here, and the function under the buffer pool called touch is trying to touch that buffer pool. We can show the stack here. You see that the whole thing, and then it called the get, the page, and then it is trying to touch. And inside the touch function, we have a call into that specific address that it's going. Actually, this is the next one. We would have to see the one that was executed prior, the command inside that function. If you want to see what the function is doing, you could unassembling the function. And let me grab this. Sorry, before we look at this, I want to grab the one that that calls the breakpoint, this specific address. Let me find this. So this is result of the unassembly. And which was it? This one. So this was the command that was trying to access that specific memory address. Okay, the memory address for the BUse1 field. All right, let me go here. So we have another hit in the touch, same function. Okay, so looks like it is doing reading the value 3 times, probably one to see the existing one, and I don't know the code here internally, but it is touching the values. Let's see in the case of the DBCC that I mentioned that it is going to call a disfavoring. Let's call this again. This, let me. It called it braked on the touch as well. Let me go. Touch again, and here it is dumping the value for me. And then after dump the value, it is again updating. It is moving one point address from one register into another one. It is updating the BUse1 value after it displays dump the value for me. So and so looks like the DBCC buffer calls the free and latch after dumps the value, and this is the one that is updating the value. If we look here, let's do it again, and let me run it again. Come on, what's going on? Probably selected more than I should. Oh, there is too many. Just one. Okay, So here are again. So let's see the, what was it, DP. I want to see the value for this. Well, actually, I could put the breakpoint. I could dump only the memory that we wanna see. Let's try the DP this one. I wanna L1. So this is the current value of the BUs one for the 5C. Let's see. What is this in decimal? 19,804. So let's run it again. So next touch, let's see if it was changed. DP this one again. No, the same value you see for the 5C. Let's try again. Now it's calling something, but it looks like it's after the, let's DP again. Yep, it was changed. Now the value is 5BCF. Let's see what is the new value. This is probably the one we will see as the result in the BCC buffer output. So 23,503. And let's try again. Dump again. Let's see if it changed. Nope, same one yet. Again, same one. And then free and latch, it is going to update it again. And if you look here, this is the 4dBF Exa. So we will probably see in the output in the management studio, we will see 23,503, but internally it's already set back to 1 hour. Let me release here. And there we go. We have the 23,503. This is really cool, isn't it? There are a lot of other comments here. All I'm doing, I'm going step by step here with the comments and blah, blah, blah. One thing that I want to highlight here is that what you could do to disable buffer pool disfavoring. If you want to, for instance, for that specific query, let's come back to the scenario. The client was complaining that the query was taking too long, too much time, and it was taking too much time because it was doing physical reads every time it ran. If you don't want it to do physical reads, we would have to make it don't trigger buffer pool disfavoring. And to don't do it, you could fool query optimizer to make it think you're actually reading less than 10% of the max server memory. And then you could try many tricks to do it. I like to use optimize for. So here I'm telling SQL that, hey, I'm going to read only 1,000 rows, or actually 100 K rows, but I'm actually reading everything. But so this is going to trigger disfavoring. Let me stop here the Windows debugger. So this will trigger disfavoring. Let's look at the X event we have. Let me run. We should see, yep, it is triggering disfavoring. Let me stop it. I don't need everything. Let me stop it. And this is triggering disfavoring because if we look here, look at how much data this is actually. Wow, this is after return only one row. To see everything, we would have to see this. This is SQL is thinking it's going to read 8 gig. 8 is more than 5, then it is going to trigger the disfavoring. So if we fool it and run this, let me resume here the X event. If I run this, you see it's not disfavoring the pages. That's nice, isn't it? All right, so what else? A few notes here. There's no buffer pool disfavoring for heaps. Okay, so if you do have heaps and the heap has 1 terabyte, it's going to remove everything from the buffer pool and replace the information with the data from the heap. The BCC would favor There is no buffer pool disfavoring for index seek if it is doing a huge range scan. So be aware of it. It's only for scans. And looks like it is driven by the query optimizer. And I said looks like because this is not documented, and most of those things I figure out by looking at the debugger and doing my own tests, right? So I might say wrong things here, but so far I'm pretty confident that I'm not wrong in any of those comments, but I might be. Every time a row is accessed in a disfavored page, the leaf page disfavored X event will be triggered. So that means that if you have a page with 100 rows, for each row that a SQL is reading from that page, it is at updating the BUse1 field 100 times, and then triggering the X event. So if you're expecting one event per page, it's not really true. It's per row in a page. And other commands may also trigger disfavoring. For instance, checkdb, it's one of them. All the reads that checkdb does are disfavored. The idea, again, it's don't mess up with your buffer pool data cache because you're running a checkdb in business hours, for instance. All right. I think that's more than what I had. And let me come back here. Some references for the reading. Paul Randall and other blog posts here. I wrote about the TempDB, the first case problem on Simple Talk. And yep, this is it. Let's wait for a few minutes. I'll be around for a few minutes and try to help you in the Q&A panel. Trying to answer your questions. And again, if you're watching the record of this presentation, feel free to send me an email. And hope you like it. Please submit the evaluations and give me feedbacks, good or bad. But they are important to me. All right. Thank you. Bye. And hope to see you all next year in Seattle. Probably, or maybe Houston. We don't know. Bye. See ya. Thank you.